In order to build circuits that manipulate, transmit, or store information, we are going to need some engineering tools to help us determine if we're choosing a good representation for the information. That's the subject of this chapter. We'll study different ways of encoding information as bits and learn the mathematics that help us determine if our encoding is a good one. We'll also look into what we can do if our representation gets corrupted by errors. It would be nice to detect that something bad has happened and possibly even correct the problem.
Let's start by asking, what is information? From our engineering perspective, we'll define information as data communicated or received that resolves uncertainty about a particular fact or circumstance. In other words, after receiving the data, we'll know more about that particular fact or circumstance. The greater the uncertainty resolved by the data, the more information the data has conveyed. Let's look at an example. A card has been chosen at random from a normal deck of 52 playing cards. Without any data about the chosen card, there are 52 possibilities for the type of the card. Now, suppose you receive one of the following pieces of data about the choice. A. You learn that the suit of the card is heart. This narrows the choice down to one of 13 cards. B. You learn instead the card is not the ace of spades. This still leaves 51 cards that it might be. C. You learn instead that the card is a face card, that is a jack, queen, or king. So the choice is one of 12 cards. D. You learn instead that the card is the suicide king. Our little blue friend is showing us that this is actually a particular card, the king of hearts, where the king is sticking the sword through his head. No uncertainty here. We know exactly what the choice was. Which of the possible pieces of data conveys the most information? In other words, which data resolves the most uncertainty about the chosen card? Similarly, which data conveys the least amount of information? Before we talk about the mathematics behind the correct answers to these questions, vote for your answers in the following poll. Mathematicians like to model uncertainty about a particular circumstance by introducing the concept of a random variable. For our application, we'll always be dealing with circumstances where there are a finite number n of distinct choices. So we'll be using a discrete random variable that can take on one of n possible values, x sub 1, x sub 2, and so on up to x sub n. The probability that x will take on the value x sub 1 is given by the probability p sub 1, the value x sub 2 by the probability p sub 2, and so on. The smaller the probability, the more uncertain it is that x will take on that particular value. Claude Shannon, in his seminal work on the theory of information, defined the information received when learning that x had taken on the value x sub I as the log base 2 of 1 over p sub I. Note that the uncertainty of a choice is inversely proportional to its probability, so the term inside of the log is basically the uncertainty of that particular choice. We use the log base 2 to measure the magnitude of the uncertainty in bits, where a bit is a quantity that can take on the value 0 or 1. Think of the information content as the number of bits we would require to encode this choice. Suppose the data we receive doesn't resolve all the uncertainty. For example, when earlier we received the data that the card was a heart. Some of the uncertainty has been resolved since we know more about the card than we did before receiving the data, but we don't yet know the exact card, so some uncertainty still remains. We can still use the formula for information content from the previous slide using the probability of the data we received to compute the information content. In our example, the probability of learning that a card chosen randomly from a 52-card deck is a heart is 13 over 52, the number of hearts, over the total number of choices. So p sub data is 13 over 52, or 1/4, and the information content is computed as log base 2 of 1 over a quarter, which figures out to be 2 bits. This example is one we encounter often. We receive partial information about n equally probable choices, each choice having probability 1 over n, that narrows the number of choices down to m. The probability of receiving such information is m times 1 over n, so the information received is log base 2 of n over m bits. Let's look at some examples. If we learn the result heads or tails, of a flip of a fair coin, we go from 2 choices to a single choice, so the information received is log base 2 of 2 over 1, or a single bit. This makes sense. It would take us 1 bit to encode which of the 2 possibilities actually happened, say 1 for heads and 0 for tails. Reviewing the example from the previous slide, learning that a card drawn from a fresh deck is a heart gives us log base 2 of 52 over 13, or 2 bits of information. Again, this makes sense. It would take us 2 bits to encode which of the 4 possible card suits had turned up. Finally, consider what information we get from rolling 2 dice, 1 red and 1 green. Each die has 6 faces, so there are 36 possible combinations. Once we learn the exact outcome of the roll, we've received log base 2 of 36 over 1, or 5.17 bits of information. What do those fractional bits mean? Our circuitry will only deal with whole bits. So to encode a single outcome, we need to use 6 bits. But suppose we wanted to record the outcome of 10 successive rolls. At 6 bits per roll, we would need a total of 60 bits. What this formula is telling us is that we need not 60 bits, but only 52 bits to unambiguously encode the results. Whether we can come up with an encoding that achieves this lower bound is an interesting question which we will take up later in this chapter. To wrap up, let's return to our initial example. Here's a table showing the different choices for the data received, along with the probability of that event, and the computed information content. We've already talked about learning that the card was a heart. The probability of this event is 13 over 52, with an information content of 2 bits. Learning that the card is not the ace of spades is quite likely, since there's only 1 chance in 52 that it is the ace of spades. So we only get a small amount of information from this event, 0.028 bits. There are 12 face cards in a card deck, so the probability of this event is 12 over 52, and we would receive 2.115 bits. A bit more information than learning about the card suit, since there is slightly less residual uncertainty. Finally, in the next section, we're going to start our discussion on how to actually engineer the bit encodings we'll use in our circuitry. But first, we'll need a way to evaluate the efficacy of an encoding. The entropy of a random variable is the average amount of information received when learning the value of the random variable. The mathematician's name for average is the expected value. That's what the capital E means. We compute the average in the obvious way. We take the weighted sum, where the amount of information received when learning of a particular choice I, that's the log base 2 of 1 over p sub I, is weighted by the probability of that choice actually happening. Here's an example. We have a random variable that can take on one of 4 values, A, B, C, or D. The probabilities of each choice are shown in the table, along with the associated information content. Now we'll compute the entropy using the probabilities and information content. So we have the probability of A, 1/3, times its associated information content, 1.58 bits, plus the probability of B times its associated information content, and so on. The result is 1.626 bits. This is telling us that a clever encoding scheme should be able to do better than simply encoding each symbol using 2 bits to represent which of the 4 possible values is next. Food for thought. We'll discuss this further in the 3rd section of this chapter. So, what is the entropy telling us? Suppose we have a sequence of data describing a sequence of values of the random variable x. If, on the average, we use less than h of x bits to transmit each piece of information in the sequence, we will not be sending enough information to resolve the uncertainty about the values. In other words, the entropy is a lower bound on the number of bits we need to transmit. Getting less than this number of bits wouldn't be good if the goal was to unambiguously describe the sequence of values. We'd have failed at our job. On the other hand, if we send on the average more than h of x bits to describe the sequence of values, we will not be making the most effective use of our resources, since the same information might have been able to be represented with fewer bits. This is okay, but perhaps with some insights we could do better. Finally, if we send, on the average, exactly h of x bits, then we'd have the perfect encoding. Alas, perfection is, as always, a tough goal, so most of the time we'll have to settle for getting close. In the final set of exercises for this section, try computing the entropy for various scenarios. Next, we turn our attention to encoding data as sequences of zeros and ones, a string of bits. An encoding is an unambiguous mapping between bit strings and the members of the set of data to be encoded. For example, suppose we have a set of 4 symbols, A, B, C, and D, and we want to use bit strings to encode messages constructed of these symbols, for example, ABBA. If we choose to encode the message one character at a time, our encoding would assign a unique bit string to each symbol. Since we have 4 symbols, we might choose a unique 2-bit string for each. A could be 00, 0, B 01, C 10, and D 11. This would be called a fixed-length encoding, since the bit strings used to represent the symbols all have the same length. The encoding for the message ABBA would be 00, 01, 01, 00. And we can run the process backwards. Given a bit string and the encoding key, we can look up the next bits in the bit string, using the key to determine the symbol they represent. 00 would be decoded as A, 01 as B, and so on. We can also use bit strings of different lengths to encode symbols. This is called a variable length encoding. So A could be 01, B 1, C 000, and D 001. ABBA would be encoded as 01, 1, 1, 01. We'll see that carefully constructed variable length encodings are useful for the efficient encoding of messages where the symbols occur with different probabilities. We have to be careful that the encoding is unambiguous. Suppose we had decided to encode A as 0, B as 1, C as 10, and D as 11. The encoding for ABBA would be 0, 1, 1, 0. Looking good, since that encoding is shorter than either of the 2 previous encodings. Now let's try to decode this bit string. Oops! Using the encoding key, we can unfortunately arrive at several decodings. ABBA, of course, but also ADA or ABC, depending on how we group the bits. This attempt at specifying an encoding has failed since the message cannot be interpreted unambiguously. Graphically, we can represent an unambiguous encoding as a binary tree, labeling the branches from each tree node with 0 and 1, placing the symbols to be encoded as the leaves of the tree. If you build a binary tree for a proposed encoding and find that there are no symbols labeling interior nodes and exactly one symbol at each leaf, then your encoding is good to go. For example, consider the encoding shown on the left. It takes just a second to draw the corresponding binary tree. The symbol B is distance 1 from the root of the tree along an arc labeled 0. A is distance 2, and C and D are distance 3. If we receive an encoded message, for example 0, 1, 1, 1, 1, we can decode it using successive bits of the encoding to identify a path from the root of the tree, descending step by step until we come to a leaf. Then repeating the process starting at the root again, until all the bits in the encoded message have been consumed. So, the message from the sheep is, 0 takes us from the root to the leaf B, which is our first decoded symbol. Then 1, 1 takes us to A, and the next 1, 1 results in a second A. The final decoded message, BAA, is not totally unexpected, at least from an American sheep. If the symbols we are trying to encode occur with equal probability, or if we have no a priori reason to believe otherwise, then we'll use a fixed-length encoding, where all leaves in the encoding's binary tree are the same distance from the root. Fixed-length encodings have the advantage of supporting random access, where we can figure out the nth symbol of the message by simply skipping over the required number of bits. For example, in a message encoded using the fixed-length code shown here, if we wanted to determine the third symbol in the encoded message, we would skip the 4 bits used to encode the first 2 symbols and start decoding with the 5th bit of the message. Mr. Blue is telling us about the entropy for random variables that have n equally probable outcomes. In this case, each element of the sum in the entropy formula is simply 1 over n times log base 2 of n, and since there are n elements in the sequence, the resulting entropy is just log base 2 of n. Let's look at some simple examples. In binary coded decimal, each digit of a decimal number is encoded separately. Since there are 10 different decimal digits, we'll need to use a 4-bit code to represent the 10 possible choices. The associated entropy is log base 2 of 10, which is 3.322 bits. We can see that our chosen encoding is inefficient in the sense that we'd use more than the minimum number of bits necessary to encode, say, a number with 1,000 decimal digits. Our encoding would use 4,000 bits, although the entropy suggests we might be able to find a shorter encoding, say 3,400 bits, for messages of length 1,000. Another common encoding is ASCII, the code used to represent English text in computing and communication. ASCII has 94 printing characters, so the associated entropy is log base 2 of 94, or 6.555 bits. So we would use 7 bits in our fixed length encoding for each character. One of the most important encodings is the one we use to represent numbers. Let's start by thinking about a representation for unsigned integers, numbers starting at 0 and counting up from there. Drawing on our experience with representing decimal numbers, in other words representing numbers in base 10 using the 10 decimal digits, our binary representation of numbers will use a base 2 representation using the 2 binary digits. The formula for converting an n-bit binary representation of a numeric value into the corresponding integer is shown below. Just multiply each binary digit by its corresponding weight in the base 2 representation. For example, here's a 12-bit binary number with the weight of each binary digit shown above. We can compute its value as 0 times 2 to the 11th, plus 1 times 2 to the 10th, plus 1 times 2 to the 9th, and so on. Keeping only the non-zero terms and expanding the powers of 2 gives us the sum 1024 plus 512 plus 256 plus 128 plus 64 plus 16, which, expressed in base 10, sums to the number 2000. With this n-bit representation, the smallest number that can be represented is 0, when all the binary digits are 0, and the largest number is 2 to the n minus 1, when all the binary digits are 1. Many digital systems are designed to support operations on binary encoded numbers of the same fixed size. For example, choosing a 32-bit or a 64-bit representation, which means that they would need multiple operations when dealing with numbers too large to be represented as a single 32-bit or 64-bit binary string. Long strings of binary digits are tedious and error-prone to transcribe, so let's find a more convenient notation, ideally one where it will be easy to recover the original bit string without too many calculations. A good choice is to use a representation based on a radix that's some higher power of 2, so each digit in our representation corresponds to some short, contiguous string of binary bits. A popular choice these days is a radix 16 representation called hexadecimal, or hex for short, where each group of 4 binary digits is represented using a single hex digit. Since there are 16 possible combinations of 4 binary bits, we'll need 16 hexadecimal digits. We'll borrow the 10 digits 0 through 9 from the decimal representation, and then simply use the first 6 letters of the alphabet, A through F, for the remaining digits. The translation between 4-bit binary and hexadecimal is shown in the table to the left below. To convert a binary number to hex, group our final challenge is figuring out how to represent signed integers. For example, what should be our representation for the number minus 2000? In decimal notation, the convention is to precede the number with a plus or minus to indicate whether it's positive or negative, usually omitting the plus to simplify the notation for positive numbers. We could adopt a similar notation, called signed magnitude, in binary by allocating a separate bit at the front of the binary string to indicate the sign. Say 0 for positive numbers and 1 for negative numbers. So the signed magnitude representation for negative 2000 would be an initial 1 to indicate a negative number, followed by the representation for 2000, as described on the previous 2 slides. However, there are some complications in using a signed magnitude representation. There are two possible binary representations for 0, positive 0 and negative 0. This makes the encoding slightly inefficient, but more importantly, the circuitry for doing addition of signed magnitude numbers is different than the circuitry for doing subtraction. Of course, we're used to that. In elementary school, we learned one technique for addition and another for subtraction. To keep the circuitry simple, most modern digital systems use the 2's complement binary representation for signed numbers. In this representation, the higher order bit of an n-bit 2's complement number has a negative weight as shown in the figure. Thus, all negative numbers have a 1 in the higher order bit, and in that sense, the higher order bit is serving as the sign bit. If it's 1, the represented number is negative. The most negative n-bit number has a 1 bit in the high order position, representing the value minus 2 to the n minus 1. The most positive n-bit number has a 0 in the negative weight high order bit and 1s for all the positive weight bits, representing the value 2 to the n minus 1 minus 1. This gives us the range of possible values. For example, in an 8-bit 2's complement representation, the most negative number is minus 2 to the 7th, which is negative 128, and the most positive number is 2 to the 7th minus 1, or 127. If all n bits are 1, think of that as the sum of the most negative number with the most positive number. In other words, minus 2 to the n minus 1 plus 2 to the n minus 1 minus 1, which equals minus 1. And of course, if all n bits are 0, that's the unique representation of 0. Let's see what happens when we add the n-bit values for negative 1 and 1, keeping an n-bit answer. In the rightmost column, 1 plus 1 is 0, carry the 1. In the second column, the carry of 1 plus 0 is 0, carry the 1, and so on. The result is all zeros, the representation for 0. Perfect! Notice that we just used ordinary binary addition, even when one or both of the operands are negative. 2's complement is perfect for n-bit arithmetic. To compute b minus a, we can just use addition and compute b plus negative a. So now we just need to figure out the 2's complement representation for negative a, given the 2's complement representation for a. Well, we know that a plus negative a equals 0, and using the example above, we can rewrite 0 as 1 plus negative 1. Reorganizing terms, we see that negative a equals 1 plus the quantity negative 1 minus a. As we saw above, the 2's complement representation for negative 1 is all 1 bits, so we can write that subtraction as all 1s minus the individual bits of a sub 0, a sub 1, up to a sub n minus 1. If a particular bit a sub I is 0, then 1 minus a sub I is 1. And if a sub I is 1, then 1 minus a sub I is 0. So in each column, the result is the bitwise complement of a sub I, which we'll write using the C language bitwise complement operator, tilde. So we see that negative a equals the bitwise complement of a plus 1. Ta-da! To practice your skill with 2's complement, try your hand at the following exercises. All you need to remember is how to do binary addition and 2's complement negation, which is bitwise complement and add 1. Fixed length encodings work well when all the possible choices have the same information content. In other words, all the choices have an equal probability of occurring. If those choices don't have the same information content, we can do better. To see how, consider the expected length of an encoding, computed by considering each x sub I to be encoded and weighting the length of its encoding by p sub I, the probability of its occurrence. By doing better, we mean that we can find encodings that have a shorter expected length than a fixed length encoding. Ideally, we'd like the expected length of the encoding for the x sub I to match the entropy h of x, which is the expected information content. We know that if x sub I has a higher probability, in other words, a larger p sub I, that it has a smaller information content, so we'd like to use shorter encodings. If x sub I has a lower probability, then we'd use a longer encoding. So we'll be constructing encodings where the x sub I may have different length codes. We'll call these variable length encodings. Here's an example we've seen before. There are 4 possible choices to encode, A, B, C, and D, each with a specified probability. The table shows a suggested encoding where we follow the advice from the previous slide. High probability choices that convey little information, for example B, are given shorter encodings, while low probability choices that convey more information, for example C or D, are given longer encodings. Let's diagram this encoding as a binary tree. Since the symbols all appear as the leaves of the tree, we can see that the encoding is unambiguous. Let's try decoding the following encoded data. We'll use the tree as follows. Start at the root of the tree and use bits from the encoded data to traverse the tree as directed, stopping when we reach a leaf. Starting at the root, the first encoded bit is 0, which takes us down the left branch to the leaf B. So B is the first symbol of the decoded data. Starting at the root again, 1 takes us down the right branch, 0 the left branch from there, and 0 the left branch below that, arriving at the leaf C, the second symbol of the decoded data. Continuing on, 1, 1 gives us A, 0 decodes as B, 1, 1 gives us A again, and finally 1, 0, 1 gives us D. The entire decoded message is BCA, BAD. The expected length of this encoding is easy to compute. The length of A's encoding, 2 bits, times its probability, plus the length of B's encoding, 1 bit times a half, plus the contributions for C and D, each 3 times 1/12. This adds up to 1 2/3 bits. How did we do? If we'd used a fixed length encoding for our 4 possible symbols, we'd have needed 2 bits each. So we'd need 2,000 bits to encode 1,000 symbols. Using our variable length encoding, the expected length for 1,000 symbols would be 1,667. The lower bound on the number of bits needed to encode 1,000 symbols is 1,000 times the entropy h of x, which is 1,626 bits. So the variable length code got us closer to our goal, but not quite all the way there. Could another variable length encoding have done better? In general, it would be nice to have a systematic way to generate the best possible variable length code, and that's the subject of the next video. Given a set of symbols and their probabilities, Huffman's algorithm tells us how to construct an optimal variable length encoding. By optimal, we mean that, assuming we're encoding each symbol one at a time, no other variable length code will have a shorter expected length. The algorithm builds the binary tree for the encoding from the bottom up. Start by choosing the 2 symbols with the smallest probability, which means they have the highest information content and should have the longest encoding. If anywhere along the way 2 symbols have the same probability, simply choose one arbitrarily. In our running example, the 2 symbols with the lowest probability are C and D. Combine the symbols as a binary subtree with one branch labeled 0 and the other 1. It doesn't matter which labels go with which branch. Remove C and D from our list of symbols and replace them with a newly constructed subtree whose root has the associated probability 1/6, the sum of the probability of its 2 branches. Now continue, at each step choosing the 2 symbols and or subtrees with the lowest probabilities, combining the choices into a new subtree. At this point in our example, the symbol A has the probability 1/3, the symbol B the probability 1/2, and the CD subtree probability 1/6. So we'll combine A with the CD subtree. On the final step, we only have 2 choices left, B and the ACD subtree, which we combine in a new subtree whose root then becomes the root of the tree representing the optimal variable length code. Happily, this is the code we've been using all along. As mentioned above, we can produce a number of different variable length codes by swapping the 0 and 1 labels on any of the subtree branches. But all those encodings would have the same expected length, which is determined by the distance of each symbol from the root of the tree, not the labels along the path from root to leaf. So all these different encodings are equivalent in terms of their efficiency. Now, try your hand at Huffman's algorithm to construct optimal variable length encodings. Optimal sounds pretty good. Does that mean we can't do any better? Well, not by encoding symbols one at a time. But if we want to encode long sequences of symbols, we can reduce the expected length of the encoding by working with, say, pairs of symbols instead of only single symbols. The table below shows the probability of pairs of symbols from our example. If we use Huffman's algorithms to build the optimal variable length code using these probabilities, it turns out that the expected length when encoding pairs is 1.646 bits per symbol. This is a small improvement on the 1.667 bits per symbol when encoding each symbol individually. And we do even better if we encoded sequences of length 3, and so on. Modern file compression algorithms use an adaptive algorithm to determine on the fly which sequences occur frequently and hence should have short encodings. They work quite well when the data has many repeating sequences, for example, natural language data where some letter combinations or even whole words occur again and again. Compression can achieve dramatic reductions from the original file size. If you'd like to learn more, look up LZW on Wikipedia to read about the Lempel-Ziv-Welch data compression algorithm. Now, let's think a bit about what happens if there's an error and one or more of the bits in our encoded data gets corrupted. We'll focus on single-bit errors, but much of what we discuss can be generalized to multi-bit errors. For example, consider encoding the results of some unpredictable event, for example, flipping a fair coin. There are two outcomes, heads, encoded as, say, 0, and tails, encoded as 1. Now, suppose some error occurs during processing. For example, the data is corrupted while being transmitted from Bob to Alice. Bob intended to send the message heads, but the 0 was corrupted and became a 1 during transmission, so Alice receives 1, which she interprets as tails. So this simple encoding doesn't work very well if there's the possibility of single-bit errors. To help with our discussion, we'll introduce the notion of Hamming distance, defined as the number of positions in which the corresponding digits differ in two encodings of the same length. For example, here are two 7-bit encodings, which differ in their third and fifth positions, so the Hamming distance between the encodings is 2. If someone tells us the Hamming distance of two encodings is 0, then the two encodings are identical. Hamming distance is a handy tool for measuring how encodings differ. How does this help us think about single-bit errors? A single-bit error changes exactly one of the bits of an encoding, so the Hamming distance between a valid binary code word and the same code word with a single-bit error is 1. The difficulty with our simple encoding is that the two valid code words, 0 and 1, also have a Hamming distance of 1, so a single-bit error changes one valid code word into another valid code word. We'll show this graphically using an arrow to indicate that two encodings differ by a single bit. In other words, that the Hamming distance between the encodings is 1. The real issue here is that when Alice receives a 1, she can't distinguish between an uncorrupted encoding of tails and a corrupted encoding of heads. She can't detect that an error has occurred. Let's figure out how to solve her problem. The insight is to come up with a set of valid code words such that a single-bit error does not produce another valid code word. What we need are code words that differ by at least 2 bits. In other words, we want the minimum Hamming distance between any two code words to be at least 2. If we have a set of code words where the minimum Hamming distance is 1, we can generate the set we want by adding a parity bit to each of the original code words. There's even parity and odd parity. Using even parity, the additional parity bit is chosen so that the total number of 1 bits in the new code word are even. For example, our original encoding for heads was 0. Adding an even parity bit gives us 0, 0. Adding an even parity bit to our original encoding for tails gives us 1, 1. The minimum Hamming distance between code words has increased from 1 to 2. How does this help? Consider what happens when there's a single-bit error. 0, 0 would be corrupted to 0, 1 or 1, 0, neither of which is a valid code word. Aha! We can detect that a single-bit error has occurred. Similarly, single-bit errors for 1, 1 would also be detected. Note that the valid code words 0, 0 and 1, 1 both have an even number of 1 bits, but that the corrupted code words 0, 1 or 1, 0 have an odd number of 1 bits. We say that corrupted code words have a parity error. It's easy to perform a parity check. Simply count the number of 1s in the code word. If it's even, a single-bit error has not occurred. If it's odd, a single-bit error has occurred. We'll see in a couple of chapters that the Boolean function exclusive OR can be used to perform parity checks. Note that parity won't help us if there's an even number of bit errors, where a corrupted code word would have an even number of 1 bits and hence appear to be okay. Parity is useful for detecting single bit errors. We'll need more sophisticated encoding to detect more errors. In general, to detect some number e of errors, we need a minimum Hamming distance of e plus 1 between code words. We can see this graphically below, which shows how errors can corrupt the valid code words 000 and 111, which have a Hamming distance of 3. In theory, this means we should be able to detect up to 2-bit errors. Each arrow represents a single bit error, and we can see from the diagram that following any path of length 2 from either 000 or 111 doesn't get us to the other valid code word. In other words, assuming we start with either 000 or 111, we can detect the occurrence of up to 2 errors. Basically, our error detection scheme relies on choosing code words. Is there any chance we can not only detect a single bit error, but also correct the error to recover the original data? Sure, here's how. By increasing the Hamming distance between valid code words to 3, we guarantee that the sets of code words produced by single bit errors don't overlap. The set of code words produced by corrupting 000, that's 100, 010, or 001, has no code words in common with the set of code words produced by corrupting 111. That's 110, 101, and 011. Assuming that at most one error occurred, we can deduce the original code word from whatever code word we receive. For example, if we receive 001, we deduce that the original code word was 000, and there has been a single bit error. Again, we can generalize this insight. If we want to correct up to e errors, the minimum Hamming distance between valid code words must be at least 2e plus 1. For example, to correct single bit errors, we need valid code words with a minimum Hamming distance of 3. Coding theory is a research area devoted to developing algorithms to generate code words that have the necessary error detection and correction properties. You can take entire courses on this topic. But we'll stop here with our basic insights. By choosing code words far enough apart, as measured by Hamming distance, we can ensure that we can detect and even correct errors that have corrupted our encoded data. Pretty neat.